hello everybody. It's day 4 of reInvent and it's lunchtime, so I'm so honored to have such a dedicated audience. There's a lot to learn today. We're also joined by an audience out in Wynn, as well as the Venetian, so hello from Mandalay Bay. I'm Dylan Tong. I'm from OpenSearch product. I'm responsible for AI and vector workloads. I'm joined by my colleague.
Hello everyone. This is Vamshi Vijay Nakirtha, working as a senior software manager, working on search at Amazon OpenSearch service. Hope you guys are having an amazing reInvent.
Yeah, so this session is about building billion-scale vector databases. We're going to be introducing 2 reInvent launches for OpenSearch, vector GPU acceleration and auto-optimize. So with that said, can I have a quick show of hands? Who here is currently using OpenSearch? All right, so a few of you. Any of you have experience with vector search? A couple, okay. So we have, so we're gonna spend some time, just a brief moment to get everybody up to speed. For some of you, maybe a refresher, but we're gonna keep it succinct, okay? So quickly, OpenSearch, it's a search and analytics engine. It's Apache open source, it's part of the Linux Foundation. And on AWS, there's a couple of flavors. One, managed clusters, where you have full control of selecting your instances. We provide automation to provision those clusters, as well as operational functionality. And then there's a serverless version, right, with auto-scaling and such. There's peripheral services, OpenSearch ingestion, for you to process and load your data into OpenSearch and OpenSearch dashboards for visualizations. People use OpenSearch for a lot of things, but there's really kind of 2 main use cases. There's one half that uses it for log analytics and observability, and then the other half is search, which is the focus of this presentation today. It could be keyword search, it's vector search, as well as a hybrid, a blend of the 2. Don't worry if you're not familiar with vector search. We'll get you up to speed, but for now, just know, hey, why do people use vector search? Foremost, it's simply to improve search quality, vector hybrid variants. It's the state of the art. It's also very versatile, right? It supports text-based search, but you can search audio, images across between the 2. There are also diverse applications. The obvious ones being semantic search, but also you can use vector search for recommendations, personalization, anomaly detection as well. Talk more about this, but it's also a key ingredient in agentic applications. A lot of people are surprised about our history, our long history in vector search. Did you know we began our journey back in February 2020? That actually predates the birth of OpenSearch. We contributed something called a KNN, K-nearest neighbor plugin, to the Elastic Open distro. And it wasn't until 2021 where OpenSearch 1.0 was released. This was a fork of Elasticsearch 7.10, and with that also, built on Apache Lucene. So we inherited a wide breadth of advanced search capabilities from that foundation. We already had a growing number of vector search users, some very large scale. For example, folks in Amazon pushing the envelope, retail, Amazon Music, Amazon Recognition. Use cases back then were around like image search and a lot of personalization. But we wanted to up-level our scalability with 1.0, so we integrated Face, which is Meta's vector search library, well known for performance and scale. I think we all remember 2023, right? That was the year of Gen AI, and with that there was the buzz around vector database, right? It was vector database instead of like KNN. So we brought our vector search capabilities to OpenSearch serverless. We became the default for Amazon Bedrock knowledge bases where people can build on Bedrock foundation models and agents and RAG, retrieval augmented generation. We created something called hybrid search. So out of the box, you can blend the traditional lexical keyword search with vector search, which turns out improves search quality. We started thinking beyond vectors as well. How can we create an AI native search engine? So we built these connectors, integrations to third-party services, OpenAI, Cohere, as well as Amazon SageMaker and Bedrock, so that we can automate the generation of vectors. Throughout the year, the deployments started getting bigger, so it became a priority to help our customers reduce costs. Cost optimizations was top of mind, building disk optimizations, tiered storage, automatic quantization, fancy word for basically compression capabilities. And we continue our journey around ease of use and AI native functionality. So not just vectors, but general AI enrichments like language detection, translation, and other automated metadata extraction. So today in 2025, naturally, cost optimization continues to be a priority. AI native, we built agentic and AI search flows into our engine. We have MCP integration, but there was a new theme. Deployments are getting larger and larger. So new theme, we doubled down on empowering scale, and that's the focus on our conversation. 2 new features focus on customers coming to us. We're growing, we're building bigger vector databases. We like OpenSearch, but please make it faster, easier, and cheaper to scale your vector database. So before we talk about these 2 features, let's take a look at a couple of customer examples and that trend towards billion scale. As mentioned before, we already had large-scale customers early on. 2020 example of that, right, is Amazon brand protection. So this is the unit within Amazon that protects our customers and partners, our retail customers and partners from abuse. And so they have a large number of automated systems in the background to detect things like IP infringement, anomalies throughout the entire product catalog. So they take the entire catalog, they basically vector encoded it into 68 billion vectors. And they're running an automation system on OpenSearch, searching for anomalies, potential IP infringement. And it's this, among other automation capabilities, enables us to detect abuse before 99% of them are even reported. So early days, a lot of the scale was driven by the likes of like Amazon, but today it's prevalent. And part of that trend, you probably heard it if you've been to the AI talks, right, is agentic applications. More and more customers building agentic features into their apps. And a good example of that is a startup called DevRev AI. We've been working with them for about a year now. So DevRev, they have this product, they call it Computer, and just think about it as your AI teammate. The challenge or the problems they're helping their customers to solve, it's an age-old one, nothing special. It's about everybody has siloed enterprise data sources, right, and tools, and they're looking to bring it together, but they're rethinking it, they're reimagining it, how we can better solve the problem with AI agents to connect, unify the data sources, drive search and automation, okay? So, and basically they're driving it specifically across product support, sales, and product management. They built it on OpenSearch. Today, hundreds of millions of vectors, and 1 million vectors changing on a daily basis. So growing really rapidly. Already great successes with their customers in support. They've achieved 85% of their tickets are resolved without human interaction. 30% cost reduction in customer support, saving their customers a lot of time. Let's dive a little bit deeper into the components of agentic systems. So imagine we have a travel system, right? Agentic features give us a conversational interface so that you can perhaps request, help me plan my trip to reInvent 2025. That request gets processed by an AI agent, typically large language model. It creates an execution plan. Usually it'll then reach out to knowledge bases, application history for context, and then compile some automation, perhaps putting together like a travel itinerary in this case. Well, you know what the saying goes, garbage in, garbage out. So when it reaches out to the knowledge bases, let's say in this case, hotel, venues, flights, if it's not able to retrieve the high quality search results, you're going to expect poor responses and automation. Vector search is the state of the art. Let's take a look at an example to understand why that's the case. So here I'm running a search on a wiki data set. I'm searching for Wild West, and you see on the left-hand side, keyword search, it's returning results like the West Virginia basketball team because it's keying in on the term West. On the right-hand side, it's semantic search using a vector-based implementation. And I'm getting like cowboys and rodeos because vector search is matching on semantic similarity. And I'm getting much better results. So if we're going to build high-quality agentic features, we need to build these vector databases or run vector search across our vast enterprise data sources. That requires scale. But easier said than done. There are a lot of challenges, some of you may know, to scaling your vector database. Let's get everyone up to speed on the basics. Highest level, you start with your content. You have an embedding model that's specially designed to encode that content into vectors. And then OpenSearch provides APIs for you to ingest and build an index on those vectors. And then that enables you to then run search queries, similarity search queries on that content. But what are those vectors exactly? The vectors are the same vectors that you learned back in physics and linear algebra, right? Main difference is back then is X, Y, Z, typically 3 dimensions. These vectors are typically over 1,000 dimensions these days, but they're just a long list of numerical values. But what's interesting is that these vectors that are encoded by these embedding models, when you measure the distance between the two, that represents the degree of similarity. So imagine I had a music corpus, I got 2 music tracks coded into vectors. If I measure, let's say, the cosine or the Euclidean distance, that's the degree of similarity between those 2 songs. If we take those vectors and we just superimpose it into 2 dimensions so that we can visualize it, it's going to look something like this scatter graph. And this arrow, pretend that's your favorite song. It's been encoded to a vector. Basically, the area around that vector, those are similar songs, the most similar songs, and perhaps the songs that you may be interested in. That's how vector search works. So you have things turn into vectors. You can measure similarity. How do you run search queries? A couple of ways. So the first one is brute force exact. So imagine you have a query vector. That's your favorite song. It's a vector. And then you have the rest of the music corpus. All the songs, they're all vectors as well. And literally, if you find a top K, maybe top 100, top 10, top K songs, known as K nearest neighbors, I literally do a comparison between everything. That query vector, compare it to one song, measure the distance, and then figure out which ones are the most closest together. Obviously, that takes a very long time. When you scale to 1 billion, it's going to take minutes at least to run a query. And that's why we have indexes. So we have these algorithms, popular one like hierarchical navigatable small worlds, HNSW, there's other algorithms, where you pre-process these vectors and you build these graph-like structures that you see here. And once you have this index, you can then do real-time queries. I can now run that top K query in milliseconds. It traverses this graph, it gets the results for you. The trade-off mainly is that it's a lot of heavy-duty processing to build that index up front. And it's also approximation, but the approximation of exact KNN is generally very close, right? You can get 0.99 or higher. Okay, so what does OpenSearch do exactly with the indexes? So it does build these indexes, but it does more to scale. So OpenSearch, the way it scales is it basically creates a search cluster. It runs across a whole bunch of servers, a whole bunch of instances. So think about a billion vector corpus. It's distributing it, partitioning it across a whole bunch of servers. And we build these indexes and host them, provide security and management, right, across all these data partitions and these indexes. When you run a search query, what's happening is in parallel, it's traversing all these indexes across all these servers. And that's how it's possible to deliver millisecond search queries on a billion scale vector data set. So that's managed clusters on the left-hand side. Serverless on the right, the architecture you can see is more fancy, but the concept in terms of how we're scaling vector search is the same, right? Across servers. The only difference here is what you're seeing is the search and the indexing workloads are separated, and storage and compute separated, and this is how it enables more auto-scaling capabilities, but same type of scaling. So, great, we could scale. We've always been able to scale, but like I said, these indexes, they require a lot of memory, a lot of compute, more so than traditional database indexes or traditional search indexes. I'm curious for the folks, especially who don't have experience, I mean, what would you expect? I mean, do you think that if I were to build a 1 billion scale index, who thinks it shouldn't take more than half a day? Who thinks it shouldn't take more than half a day? Okay, I probably gave it away. But yes, it takes more than half a day. Generally, in the wild, it takes days. So that's tough, right, in terms of productivity and your innovation or velocity. Typically in the wild, there's variables, but it typically takes days. And the catch is not just a one-time thing. It's not like build an index, okay, it's going to take a couple of days. It's just a one-time thing. There's a life cycle to it. These indexes are special. You have to rebuild them more often than your traditional database index. So first of all, HNS-W, it does degrade when the data changes. So you have a agentic app. It's very dynamic, right? The vectors, the content is changing all the time. Well, you're going to have, you got to mitigate the search quality degradation and rebuild that index. If you change that embedding model as well, it means you're going to have to regenerate the vectors and rebuild that index. So, when can that happen? Maybe you're switching between OpenAI, Anthropic, Cohere. Okay, you're going to have to rebuild that index. These vendors, they produce multiple versions of their model every year. That happens, 1 to 4 times, I think, typically per year. You want to benefit from the latest and greatest, you're going to have to update, rebuild your index. But it could be even more frequent than that, especially for special use cases, maybe like personalized search. Taking an example from Amazon Music. So Amazon Music, this is a streaming service, and when you see, if you've used it before, you may see, hey, because you listen to this song, we think you may be interested in these other songs. That is powered by vector search. So they have this recommender type model. It's built for vectors, generates vectors from their song selection, all the older music tracks. Over 1 billion vectors running in OpenSearch, and they use that to power those recommendations. If you're familiar with recommendations, personalizations, it's important for you to continually retrain or fine-tune those models on your users' latest behaviors and profiles if you want to have the best recommendations. Their case, you need to do it on a daily basis. So there's these use cases, you have to rebuild the indexes on a daily, weekly, or monthly basis, depending on your use case. What happens if that takes days? It's going to be tough making your SLA, or it's going to be a burden. Also, for those, on the managed cluster, your search and your indexing workloads are also running on that same infrastructure. Well, you have these graphs that take a lot of RAM, a lot of compute, and at the same time you're running search, there's a tug of war going on, right, for these resources. And there's going to then be also the challenge, right, operationally to maintain good search times. So there's also that challenge, right, in terms of separation of workloads. So these are the problems that our customers are facing at large-scale vector search systems. Building, maintaining can take days. It's tough to maintain, right? Vector ingestion can impact search speed. So we need to help our customers maintain their innovation velocity, their productivity, and build responsive applications. So we knew that one potential solution could be GPU, right? So we all know GPU from things like computer graphics, right, in gaming and AI. And what's going on in those cases, it's a lot of vector math. It's really good at that. So we knew that there's a lot of potential. So we worked which is the same as what's going on with vector search and building these indexes. So we worked with NVIDIA, and NVIDIA has this library called QVS, a bunch of vector algorithms optimized for GPU. And we worked with them to explore things like they had this algorithm called Kagra. And so we looked at that, and we worked with them on enhancements as well because we wanted to be able to build on Kagra, but we want to run those indexes in RAM, right? And run search in RAM still so we can run other workloads. So we worked with them on enhancements in that area, and we want it to run in Face. So build on Kagra, transfer to RAM, run within Meta's Face libraries. With those enhancements, we also ran a whole bunch of tests that you see here. Data set sizes running from 1 million, 10 million, 100 to 1 billion, different vector data set sizes. So we start off by creating first a baseline, right? Let's just run it on CPU. We build the index. We run something called a merge command if you're familiar with it, but that's important. Basically, you build the index, and with Lucene, right, you need to do a merge to ensure that afterwards the index has high search performance. So we include that in the test, and you can see here, it takes a long time. Once you get to the large scale, the 100 to the 1 billion cases, it now takes over a day to perform that on a right-size cluster. What happens when we add GPU instances into the mix? Huge difference. See a speed up ranging from 6 to 14 times. And there's also the cost of building that index, the cost of that building that index, the task, is also much lower cost because it's doing it so much faster and so much more efficient. Even though we have more infrastructure. Not only do we have a CPU infrastructure, but we added additional GPU infrastructure. So it's more, but because it does the task so much faster and so much more efficient, you can see cost savings from 6 to 12x. It's substantial. The cost savings are a little bit more easier to understand from a serverless standpoint. Remember I said that the search and the indexing workloads are separated on serverless. So what that means is that when you get your bill from serverless, you actually see a line item. This is your index cost. This is your search cost. And along with that cost, it's going to say, okay, you use this many OCU hours. That's OpenSearch compute units. So with the same test, basically you're seeing, let's look at the 113 million case, 1,024 dimensions. It's saying that you use 2,721 OCU hours. That's a lot. It's basically a lot just to build that big index. Well, when we add GPU, and I converted the GPU cost to OCU, so it's kind of easy to understand. Again, we're adding GPU infrastructure, but it's reducing the CPU utilization, and again, it's tremendous. So if we look at the 113 million test case, we brought that down to 104.5 OCUs to accomplish that task. That's 8.9 times cost reduction. To put that in hard numbers, in US, North Virginia, the cost for one OCU hour is 24 cents. If we do the math, basically we're going from, was it $853 to $73. So that's huge. Now it's manageable, right? If you're at that scale, you have to rebuild the indexes. Now the cost is manageable. The other thing we want to look at is we want to simulate a dynamic application. Now, we have an agentic app. We have a whole bunch of concurrent users who are searching for things, but at the same time, they're also updating, inserting content, so we're indexing at the same time. As I said, the search speed can be impacted. So this test is demonstrating that, right? We're doing a mixed workload. Mixed workloads. On the y-axis, it says indexing clients. Just think of that, we're ramping up the number of writers, like the amount of updates and indexing operations on the system. And in the line, what we see is expected, the CPU utilization on a cluster is increasing. And the bar graph is showing that the search latency as a result is increasing because there's that pressure competition between CPU and RAM between the reads and the writes. when we add GPU and we offload to CPU, right, we bring down the CPU utilization and the search latency now becomes much more manageable. Now it's a much better user experience. We're back to good latency. So we proved it out. Hey, a lot of potential for GPU, but there's one more challenge. Exactly how are we going to integrate GPU into OpenSearch? The obvious thing is, okay, we just support GPU instances, right? That's the obvious. That would be really easy. But if we did that, that would cause economic problems. Let's take a look at an example. Let's say we did that. Let's take a look at a deployment for 1 billion vectors, 1,024 dimensions. We're going to apply aggressive cost optimizations. We use binary quantization, basically 32x compression, to make the cluster as small as possible. On CPU, what that means is that it's going to be memory bound generally. We need 3x, more than a terabyte of RAM, right, for good performance. So we use 3 of these R8 instances. Okay, so that's going to cost some amount. So let's say if I wanted to bring GPU, I'm going to have to pick a GPU instances, use GPU instances. We use the G6s because those are very cost effective, but they're not optimized for RAM capacity. So I need 6 of those now to meet the RAM requirements. That's 2.4 times the cost. I got GPU now, that's great, but it's a huge premium for the speed gains. And I'm not always indexing, so that's the problem. So we knew that for this to be practical for most of our customers, we have to do things differently. So working backwards from the ideal scenario is, want to let you continue using your existing collections and domains with, running on your CPU instances. You want to use the same APIs. We don't want to change any of that, but can we bring the GPU to your CPU-based clusters only when you need it, and you only pay for value, only when you benefit from the indexing to GPU acceleration. And we did that. We did just that. Exactly how did we do it? Behind the scenes, we built this system that you see here. So number one, that's you as a user. There's no change to how you use OpenSearch. You're indexing vectors, same thing. You use the index API to re-index bulk. But what happens is when you have it enabled and we detect that now you have high write throughput, let's say you're writing 10,000 vectors per second, it's going to trigger a configurable threshold. And we are then going to allocate GPU instances to your CPU cluster, offload those graph builds. We, behind the scenes, are going to manage a warm pool of GPU instances for you. You don't need to worry about that. Multi-tenant, because you then benefit from the economies of scale, but we do a single tenant secure assignment so that it's only your workloads running on those instances. We basically automate the scaling for you. When you're done with the GPU acceleration, we return it to that pool. So we do all that behind the scenes so that you only need to pay for what you benefit from. From your standpoint, it's as simple as a light switch. You just enable it through the APIs, CLI, through the console like you see here, and you pay. It's serverless. It doesn't matter if you're using managed clusters or OpenSearch serverless. This acceleration is serverless GPU. And it's at 24 cents basically per OCU hour in North Virginia. So pretty much same as the standard indexing OCUs. So that's it, GPU accelerated vector indexing. Building these indexes much faster, but there's actually more to it to create these production systems. So with that, my colleague is going to talk about what else we need to do.
Thanks, Dylan. So my colleague has covered about the basics of vector database, generating the vectors, ingesting the vectors, and building these indexes so we can enable the real-time vector search for the end customers. But there is more to it. There's one more important aspect in this flow. Can anyone guess? It's the index configuration and optimizing the configuration. So to build any vector index, you need index configuration. This index configuration determines the search quality, cost, and speed of your indexes, of your applications. And optimizing these indexes can cut down the cost by a third of the total cost. And this is more evident as the scale of the vector workload increase. So let's take a look at the scale. So on the x-axis, I have the number of vectors. On the y-axis, I have the memory footprint. As you see, from 10 million onwards, the memory footprint reduction is almost 75%. So at 10 million, we almost see around 300 gigabytes of memory footprint savings. At a billion scale, we are able to see around 3 terabytes of memory footprint savings. So it's very important to optimize this index configuration. Well, what are these index configurations? So Amazon OpenSearch service has a rich feature set of index configurations and its tunable parameters that lets our customers make a very smart trade-off between what should be my quality, cost, and speed. So on x-axis, we have the search quality, which we call recall. On the y-axis, we have the latency. As we trade off between this quality and the latency, you could see those purple bubbles. All of those are index configurations. And each index configuration have a tunable parameters. On a high level, you can think of these tunable parameters into like 3 categories. One category helps to determine the type of algorithm. Is it like HNSW, as Dylan talked about it? That's graph-based algorithm. And another one is IVF, which is a bucket-based algorithm. Similarly, the second kind of category is the compression techniques. Like, do you need a binary quantization, scalar quantization, product quantization? Like, you can achieve the compression from 2x all the way to 64x, which helps to trade off the quality for the memory footprint. Similarly, the third category talks about the mode of operating these graph data structures. Do you want them in memory or on disk or somewhere remote, like S3 vectors? It helps to trade off the latencies. Our customers love these trade-offs. It helps them get best of their hardware resources, but it's not straightforward, right? It needs some expertise in KNN vector search algorithms, and also it takes time. So the experts would generally start with picking up the configuration, algorithm configuration, the quantization technique, and the mode of operating these algorithms. And then you would build these indexes, have your ground truth, so you would evaluate what is my quality, latency, and then the cost. And if it doesn't meet your requirements, we adjust and repeat. So this can take time. Let's take an example. So let's say I'm building an application which needs 95% accuracy. So I pick up a 32x compression, the binary quantization, which is very popular, and I build my indexes, I run my quality check, and then I realize, oh, it's 90%, it's not 95%. So maybe I should reduce my compression level so I can preserve more vector precision and I can get better quality. But the trade-off is in the memory. I might need to pay more memory. So I'll go back, reduce my compression techniques to 16x, and then rerun the builds, and then validate what is my recall quality. Maybe this time it's 93%, but still not meeting my requirement. I go back and then make it 8x, so on and so forth. I repeat this process, build the index, and validate my configuration to check whether it meets my requirements or not. And one more important aspect, there is no one optimal configuration that works for all the use cases. The index configuration is more subjected to the data set and the business requirements. So let's take an example. So let's say I'm building a recommendation systems for an e-commerce application. I need a high performance vector database. The quality has to be better. The latency has to be near single digit or double digit milliseconds. So I would need something like the hyperparameters. It could be like in memory, and then I have a GNSW algorithm and different parameters. And similarly, I have another application where I'm building a search application for my company for internal usage. I need quality, but I don't need a single digit millisecond. Even 100 millisecond or 200 millisecond is fine. So then accordingly, I will choose my hyperparameters configurations. Or maybe you're trying to have something in between, right? So arriving at these optimal configurations takes time. So how did we simplify this? So Amazon OpenSearch Service wants to simplify the onboarding experience. Whether you may be building a POC or a large vector workload, we wanted to reduce the expertise needed to build and manage these indexes. So what we did is we built an auto optimization framework, and we let the framework learn all of these techniques, all of these algorithms, parameters, the tuning configurations, so we could do the heavy lifting for you. So now it gets simplified. All a customer needs to provide is what is my acceptable search quality and what is my acceptable search latencies. And behind the scenes, Amazon OpenSearch Service will take your data, will take your business requirements, analyze your vectors, run a bunch of hyperparameter optimization jobs, and get you the recommendations. And the good thing is, we also provide you we are very transparent. We provide you all the details. We provide you a detailed report for each of the recommendation. You can look at your performance metrics, like what is my recall, what is my memory footprint. You can look at your algorithms, algorithm parameters, hyperparameters, compression levels. So all the focus can now be on the recommendations, and then you can pick up your best recommendation. And the best part, our customers don't have to manage the infrastructure. Amazon OpenSearch Service has a serverless auto optimization framework. It's built on a serverless fleet where we parallelize all of our hyper optimization jobs, and we build it under an hour. Under 1 hour, we are able to build the optimizations. We are able to provide you the recommendations, optimizations as recommendations. So with this, one, we cut off the expertise required. All we need to do is to focus on the business requirements. Two, we cut down the time. We are able to give you recommendations under an hour. So all the iterations that you need to do for a POC, so we are doing it behind the scenes for you. So under an hour, you get your recommendations. And three, we're cutting down the cost. You don't have to manage the infrastructure needed to run these experiments, the POCs, to get to the production. Let's see it in action. Okay, so once you land up on your OpenSearch service, on the left-hand side, under the ingestion, we added a new entry, vector ingestion. For the purpose of the demo, I am going to play a role of a search engineer who is trying to upgrade application from a lexical search to a semantic search like vector search. So we have the workflow explaining the process here. Step one is preparing data set. So I have all my documents. It could be text, image, audio, or video. So we take all of the documents, pass it to the embedding models, generate the vectors, and have them in the S3 bucket. Then step two, I provide my business requirements. So I need X search quality and Y latency. So I provide the recommendations. And step three, we would have the recommendation. I provide the requirements. And step three, we would have the recommendations available. And step four, I can choose one of the recommendations and say build index. So we ingest and accelerate the building process with GPU acceleration. So let's create one ingestion job. So let's say as a step one, we have to configure the data source and destination. So my data source is an S3 bucket, and US East one. So within this, I have the data folder. So let me select my folder. And then I need to provide the destination details. So this could be your Amazon OpenSearch domain or Amazon OpenSearch collection. So I'm going to pick up my domain. So I'm going to pick up of the domain, and then you configure the permissions, and then go to the second step. As part of the second step, I configure my index. So here, I have my vector field named train, and my space type is inner product, and the dimension is 768. So this particular thing has to match with what we have in the S3 bucket. So when we generate those embeddings from the model, so I'm putting the name of those vectors as train, and then having the embeddings there. So the mapping would be something like train, and then the vector. And the dimension of the vector is 768. And the space type you could determine from the model when you run it. So it tells you what is the space type. And then this is the best part of this. So here I focus on the requirements. So like I said, if I'm building an application which needs high performance, I would choose something like 0.95 recall and have fast. Fast means within a single digit or under 50 milliseconds latencies. So it's like a high performance application. Similarly, if I want to build something like a chat application, maybe this quality, 90% quality is good, and it could be modest, so it's more like a balanced profile. So accordingly, based on your application, you could provide the requirements on this page. And then here you could you can review the configuration and then click create. So once you click on this button, so we are sending a signal to our backend system to run the optimization, hyper-optimization jobs, hyperparameter optimization jobs, and provide the recommendations. So this would take between 30 minutes to 1 hour. So for the purpose of the demo, I already had a job that is run, so let me show the recommendations from that job. So once the job is complete, so you would have a banner saying it's completed. It says that you are in which step of the workflow. So right now, I am at the recommendation step. So this is how my recommendations would look like. So I have 3 recommended configurations. It took 42 minutes to run this job, and the configurations, the business requirements were 90% recall and fast. So when we project our recommendations, we always optimize them based on the cost. So we sort them based on the cost. The first recommendation is a baseline for us. So we are able to achieve around 0.92 recall, and then between option 2 and option 3, I'm able to get more recall, but there is an increase in the memory footprint. So this is the trade-off I need to make to get a 0.5% better quality. Will I be okay to have 50% memory footprint? Or maybe I need 3% more better recall, and I'm okay for having 100% memory footprint, or 2x memory footprint. So you can look at the performance metrics on this page. And let's say you want to understand what was actually the process, what were the algorithms options that were picked up behind each of this recommendation. You can also look at the detailed report. So you can click on the report. So you can look at the engine parameters, the mode, and the engine. So here we are picking up in memory because the business requirement was fast. So to make it a single digit millisecond or a double digit, we have to host the vector data structures in the memory. And then we are using the FIAS algorithm and FIAS library, and the algorithm is HNSW. So here we talk about all the hyperparameters that we picked up and the value of the parameters and what each parameter means. So on a high level, HNSW has different parameters like M, EF construction, EF search, which talks about how many edges I need to establish between the nodes, or how many neighbors I need to consider while I am walking through the graph. So the more the neighbors, the better the quality. The more the edges, the better the quality, but at the cost of memory footprint. So these are all the evaluations we do behind the scenes and come up with these parameters. And then here we are using the binary quantization technique, the 32x compression. So essentially we are taking your dimension, which is 32-bit floating vector, and making it to a single bit. So likewise, I can go to different recommendations and then look at the configurations. the engine parameters, algorithm parameters, the compression parameters. So here it's using 16x compression. So that's why the memory footprint has been increased, because previously the baseline is using 32x. But in the second option, we are able to recommend you the 16x compression because it gives you around 0.3% better recall. So we look at all these options, the recommendations, and for me, and for my application, I'm willing to have option 1 because my accuracy requirement was 90%. This is well above my requirement, and it is fast, so I'm going with option 1. And then you click on the build index. So as part of the index, provide the name of the index. So this is the index which we are going to create on your destination. So on the, like in this case, I have chosen the Amazon OpenSearch domain. So on that particular domain, I'm going to create this index with the following configuration, the option 1. So finally, all the configurations that we see in the report, it boils down to the JSON configuration. So this is how it looks like. It talks about the files, it talks about this construction parameters, inner product, it talks about this compression level in memory. Yeah, so we are able to finally get to the JSON which OpenSearch can understand. And let's say along with vector fields, you also have other fields. Maybe you have some metadata like text, date. You can add your fields here. So let's say I have a field text. So I'm going to add a text field. Similarly, I have a date field. So on. So you can add your fields, and this is, so when you are ingesting, we look for these fields on your documents in S3 bucket. And then I can click build index. The most important thing here is the GPU acceleration. So as my colleague talked about, so building these graphs are compute intensive operations. So one part of it is ingesting into the destination, but the second part is once it arrives at the destination, the GPU acceleration speeds up the building process. So we can enable the search applications faster. So you could enable from here. So it takes you to the edit cluster page, and then under the vector database features, we have the option to enable or disable the acceleration. So for this particular destination, I already had it enabled. So I can enable this and then click on dry run. So I need to choose a new generation instance type, and that's it. So the dry run, it evaluates all the configurations, just make sure everything is correct, and then it clicks the update process where the flag gets enabled. And then you can click on the build index. So once we click on the build index, what happened behind the scenes is we kick off the ingestion workflow. So we have an ingestion pipeline that takes the source, in this case your S3 bucket, the sink, which is our destination, which is our domain or a collection, and then stream the data. And the ingestion pipeline is also serverless. So it can, based on your volume of your data and based on how much your destination can take, it can increase or decrease the computing units. And then once the ingestion is done, so you can look at all the job configurations here. You can go to the vector ingestion page and then look at all the completed jobs here. So for the auto optimization, there are multiple states like completed and then active or failed. For the ingestion status, right now I just triggered the ingestion, so it's in the creating state, and then it becomes active. And once the ingestion is completed, we stop the pipeline. So with this, we are able to, within few clicks, we are able to take your data, take your business requirements, run the hyperparameter optimization jobs under an hour, provide you the recommendations. So you can look at your recommendations and choose the best recommendation. And then within a single click, we are able to take the index configuration, create an index, and stream your data to the destination, all behind the scenes without having to, without any manual intervention. So this is how, with the auto optimization and the GPU acceleration features, we had tried to simplify the onboarding experience for Amazon OpenSearch service. So this concludes my demo.
I think we have some time to maybe take a few questions a little bit early. What do you think?